So, what if the thing that decides between life and death wasn't a giant, expensive helicopter, but something a rescuer could literally carry on their back? Today, we're diving into a technology that's totally rewriting the rulebook for rescue missions, a drone swarm that can get to places and people that are completely unreachable. Just picture it for a second. A climber, badly injured, stuck on a tiny mountain ledge. Or maybe a sailor thrown overboard into rough seas. Or even a firefighter cut off by a wildfire raging through a dense forest. In every one of these cases, the clock is ticking, and time is about to run out. You see, in situations like these, our usual rescue methods just hit a wall. The weather might be too gnarly for a helicopter to fly, or there's just nowhere for it to land. Sometimes the wind from the rotors itself is too dangerous. So that leaves the ground team. Total heroes for sure, but in that kind of terrain, they're moving at less than 3 kilometers an hour. They're just not going to make it in time. And this is the critical question, isn't it? What if that massive power you need for an aerial lift didn't have to be flown in from miles away, but could be walked in right to the edge of the problem? What if the answer wasn't one giant, complex machine, but a whole team of smaller, smarter ones working together? To really get why this is such a game changer, we first need to talk about a concept that pretty much haunts every single first responder out there. It's called the golden hour problem. The golden hour is this brutal, unforgiving clock. After someone suffers a major injury, their chances of survival just plummet with every minute that goes by. So for search and rescue teams, their entire mission becomes this desperate race against time to get medical help to the victim and then get the victim to a hospital, all inside that 60-minute window. And this slide right here, this shows you the logistical gap that rescue teams are always up against. Ground teams are amazing, but they're limited by human speed and just treacherous terrain. Helicopters, on the other hand, are fast, but they're often this all-or-nothing tool. They can either get to the target or they can't. And that gap between where a helicopter can't go and how fast a person can, that's where lives are lost. So the big question is, how do you bridge that gap? Well, you don't. You create something completely new. You create what is basically a backpack aerial ambulance. Now, your first instinct, and mine too, probably, is to just say, well, build a bigger drone, right? A single, super powerful machine that can lift a person. But the thing is, that just leads you right back to the same problems as a helicopter. It's too big, it's too heavy, and you still can't get it into those truly remote spots. No, the real paradigm shift here is to stop thinking about a single aircraft and start thinking about a coordinated team. The solution isn't about brute force, it's about distributed intelligence. And this is the core idea behind what's called Distributed Aerial Search and Rescue, or DAS-SAR. So instead of one huge drone, you use a swarm of smaller but still very powerful drones that are all physically tied with tethers to the payload, the stretcher. The key is each one of these drones is small enough to be carried in a backpack by one person. When you look at it this way, the advantages are just massive. That giant drone, it's a single point of failure. If one little thing goes wrong, the whole mission could be scrubbed. But the DAS-SAR swarm is what we call fail operational. That means it can literally lose an entire drone and the others just compensate and carry on safely. And the deployability, it's a total game changer. A team can hike up to some narrow, impossible ridge and assemble this incredible heavy lift machine right there on the spot. Okay, so the concept is absolutely brilliant. But how does it actually work? How do you get 6 totally independent drones to work together like one single muscle? Well, this is where the science gets really, really cool. Think about it like this. Any object floating in space, like a stretcher, has what we call 6 degrees of freedom. It can move forward and backward, left and right, up and down, and it can also rotate in 3 ways: roll, pitch, and yaw. So to have total, perfect control over that stretcher, you need at least 6 different points of force. And that's why the system uses exactly 6 drones, 1 for each degree of freedom. But just lifting the stretcher is only like half the problem. The real challenge is controlling it once it's in the air. A stretcher hanging from 6 different tethers can act like this incredibly complex pendulum. One gust of wind could send it swinging wildly and dangerously. So managing this swing angle becomes the #1 engineering problem they have to solve. And the solution here is it's so clever. Most systems like this would use what's called impedance control. Basically, each drone tries to rigidly hold its position, fighting against any outside force. In a swarm, that would be a total disaster, just a constant, violent tug of war. Instead, DAS-SAR uses admittance control. So rather than fighting a force like a gust of wind, each drone admits it and complies, moving just a little bit. It's exactly how you see ants carrying a big leaf. They all work together smoothly instead of fighting each other.
Now, of course, this technology doesn't exist in a bubble. To really understand how big of a deal this could be, you have to look at the massive companies already in this space, and at the cautionary tales, the ghosts of startups who have tried to do big things and failed.
On one side, you have what I like to call the flying trucks. I mean, these are incredible machines from companies like Malloy and Griff that can lift hundreds and hundreds of kilograms. They're perfect for moving supplies for the military or doing industrial work, but they're enormous. You can't hike one of these up a mountain. They can't solve that last mile extraction problem.
And then on the other side, you have the startup graveyard. These are companies with brilliant ideas, hundreds of millions in funding that still failed. You had Lilium, who just slammed into a physics wall with battery tech. Guardian Agriculture, who had a great hammer but couldn't find a market nail that made sense. And Airware, who tried to build all their own hardware from scratch and just couldn't compete. Each one of these is a huge lesson for any new company in the space.
And this is what is so important to understand. DAS-SAR is not trying to compete with those flying trucks. It's creating an entirely new category. Man-portable heavy lift. It's not about replacing those giants. It's about going where they physically cannot go, period. So let's talk numbers. Let's get down to the nitty-gritty. What's it going to take to make this vision a reality? And what can it actually do out there in the real world? Well, the estimated seed funding to get a full-scale system that's actually rated to carry a person is about 1.3 million euros. Yeah, it's a serious investment, but that's what it takes when you need top-tier engineering talent and super reliable industrial-grade parts. The system is being built for a target payload of 115 kilograms, which is about 250 pounds. This is the sweet spot that covers the weight of an average person, plus all the necessary gear, the stretcher, the medical equipment, to keep them stable on the way out. And here it is. This is the number that matters most to the rescuers on the ground. The calculated operational radius for a round-trip extraction mission is just under 4 kilometers. Now, that might not sound like a huge distance, but that's the whole point. It's the perfect distance. It is the lifeline that bridges that logistical gap, letting a team launch from a safe spot and pull someone off a ridge 3.8 kilometers away, a distance that would take a ground team hours and hours to cover. So in the end, the whole idea here isn't about building a better tank, one single powerful but vulnerable machine. It's about embracing the resilience of an ant colony, a distributed, adaptable swarm where the group is always stronger than any one part. It really makes you wonder, doesn't it? What other impossible problems out there could we solve if we stopped trying to think bigger and started thinking together?